Okay, I'll remake my histograms and stuff, but here's the distribution of scores and whatnot. I mean, your grades have been posted. All right. The median was okay. So I took everybody's scores and then I just added 8 points to everybody's score. Okay, so that's how we ended up with a few scores over 100. And after adding 8 points to everybody, the median score is 80. Okay. Students ask if I curve. I personally don't like the idea of curving because that effectively pits you against other students, and I think everybody's performance should just be against the test. And so, after, during the grading process, I realized, okay, so, maybe a couple of the questions might have been a little bit tricky and things like that. So that's why I decided to add 8 points to everybody's scores. But that's what we have. I do want to just say a few things, okay? And you're gonna hear me say this a lot, okay? Don't tie your self-worth or perception of yourself or whatever to scores on any exam or grade or whatever, okay? Does it feel good to get good grades? Yes, it does, okay? And I understand that. And does it feel bad to get bad grades? It does, okay? And I also understand that. But don't become sad or whatever because your score on some test in some class that doesn't matter, it wasn't as high as you want it to be, okay? There's a few other notes of consolation in that, as far as midterms go, I think this one is weighted pretty lightly. It's 15% total of your grade, okay? Which means there's 85, like your entire grade, I'm pretty sure that's what I have in the syllabus, right? The other 85, what? 20? Okay, all right. Okay, so I said the wrong thing. Okay, 20% of your grade. It's not worth a ton, okay? There's lots of other points to make up, lots of other places to make up points. Life will be okay, all right? I promise. And okay, are there any questions? My intention is to have the TAs return them to you next week in section. Okay, so go to section, get your exams back. I'm returning the exams to you. There's a degree of trust here. Okay, don't post pictures of the exam on some website. Don't give it to other students and other things in other classes and things like that. Most of the exams I actually keep for myself, but this one exam I do the practice quiz or the old exam and I return them to you guys. But please also don't be posting this on websites and stuff. I just ran a check on Course Hero for my own name, and it always kind of makes me a little upset that students don't respect what I've asked. So if I just did like cite Course Hero and I search for Miles Chen, there's going to be like, this came up from my 102C, and it clearly says in the, oh, it's because I was searching for myself. It says I reached my limit. Okay, but anyway, it says copyright Miles Chen for personal use only, and then in the notes it says don't post it, and then people post stuff like this. Okay, it is, just to let you know, it is a violation of the Student Code of Conduct, and you can be taken to the dean's office, and you'll have the hearing and stuff you know, if we decide to pursue these things. So don't do stuff like that, okay? Anyway, that's all I want to say about the exam. Yes, question.
Does the grades that we saw already reflect like the 8
It does already reflect the additional 8 points. It does, okay? Yeah, it'll be okay. All right. There's lots of other points to be made up if you didn't do as great as you would have liked. Okay. Today we will take a look at floating point numbers. All right. So let me get my camera here started, and this we'll actually use that. Okay. So all right. I think at the very beginning of the course I said this class is kind of like 2 classes in one, okay? So we finished the first half, okay? The first part, which was a lot of like R programming and R nitty-gritty details and things like that, okay? Now we are transitioning over to numeric methods and computational statistics stuff, okay? And central to that is we have to understand floating point numbers, okay? So floating point numbers is how a computer represents numbers, okay? Which seems weird. You're like, the computer shows numbers, what's the big deal, okay? So we'll just talk a little bit, right? Okay, so in math, you guys learned about real numbers. And you know, they're everything on the number line that goes from negative infinity to positive infinity, okay, as opposed to like complex numbers or integers or things like that, right? You got your natural numbers, and things like that. But anyway, as far as real numbers go, we have infinitely many real numbers. And as far as, you know, if you pick any 2 spots on the number line, like 0 and 1, there's also infinitely many values, and it's infinitely, and you can't even count those values. There's just infinitely many of them, okay? And many of these values will have an infinite number of decimal places, okay? Things like pi and e, square root of 2. A lot of these things have infinite numbers of values after the decimal point. And so if we wanted to write these out in decimal form, it's not possible to get an exact representation, right? So for example, if you wanted to represent pi on a piece of paper, maybe in high school you just use 3.14, but that's an approximation, right? Even if you have a bunch more decimals, 3.14159265535, whatever, that's still just an approximation. And even if I used 1,000,000 sheets of paper and filled it out with like, I don't know, 1 billion decimal places, okay? That is still just an approximation, okay? We cannot get the exact representation because there's infinitely many decimal places, right? And so the fact that we can only get approximations have some profound effects on certain math rules that we have taken for granted, okay? So when we are dealing with the computer, we cannot represent an infinite number of decimal places, okay? We have a finite amount of storage, a finite amount of memory, and so it is not possible to do an infinite thing, right? You might have the computer solve out to the billionth digit of pi, but that is just a finite approximate representation of the value pi. And you've used up a lot of memory and a lot of storage just to have those billion decimal places, okay? So I'm going to just start off with a tiny example here, and let me see if I can blow up this camera. All right, okay, so I don't know, so I've got this little calculator here. This is just a very simple calculator, and I don't know if you've ever did this as a kid, but what would happen if I do 10 divided by 3. What will the calculator show? 10 divided by 3 will give me 3.33333, right? This calculator is only able to show 8 digits. And so this is an approximate representation, because the true representation would have 3's going off to infinity. So 10 divided by 3 gives me 3.333. Okay, what happens if I take this number and I multiply it by 3? Yeah, you guys know exactly what's going to happen. I say multiply it by 3, and I hit that, and I get 9.99999, okay? And so, if somebody's understanding of math came from a calculator, they would walk away with the wrong interpretation that 10 divided by 3 and multiplied by 3 is not equal to 10, okay? And here's another thing, right? So here I did 10 divided by 3 and I multiplied by 3 and I got something different from 10. On the other hand, if I changed those operations, if I did the multiplication first and then the division, so if I did 10 times 3, this seems stupid, I would get 30, okay? And if I do 30 divided by 3, I get 10, okay? And we get what we expect. 10 times 3 divided by 3 gives us back 10, okay? But we see on the calculator, if we do 10 divided by 3 multiplied by 3, we don't get 10 back, we get 9.99999, okay? And we can understand, like, this kind of makes sense to us because we get like, oh, all right, this calculator can only represent 8 digits at a time. And that's basically what is happening, what happens on the computer as well. Okay, a lot of your modern calculators, so this is, I had to like find this old cheapy calculator to do this because a lot of your modern scientific calculators have like things built in to say like, oh, we know what you're talking about, that 10 divided by 3 times 3 gives you back 10. You know, other things like if I did, I don't know, if I did like 2 square root and I multiply it by itself, I'm not going to get 2 back, things like that, okay? And so, you know, a fundamental rule, here we did x divided by a multiplied by a, that's not equal to x times a divided by a, okay? So, so these, that, you know, associative rule, these are all things that we've learned and taken, like, these were probably ingrained to us somewhere in elementary school, 6th grade or whatever. You learned all of these things. These do not apply when we're dealing with finite representations of real numbers, okay? In real numbers, you have infinitely many decimal places, and they are the same, okay? All of these rules work out. When you can only store like 8 decimal places or store a finite number of values in your computer, these rules fall apart, okay? And so just to kind of further illustrate this, and you can try this on your computer right now, okay? Create a value x and put 0.1 in it, all right? Create a value y and put 0.2 in it. And create a value z and you put 0.3 in it, okay? All right, so what will happen if I do x plus y? X is 0.1 and y is 0.2, okay? Okay, you get 0.3, all right? This is not a trick question, this is, that's what we have. Okay, and if we ask, okay, what was z again? Z is 0.3. And then for real, if I do, okay, what is x plus y equal to z? I'm just testing for equality. Is 0.3 equal to 0.3? This comes back false, okay? And this is not just some trick I'm doing here on, those aren't in any order, just so don't worry about, okay, but if I did like 0.2 plus 0.1, or here, I'll just go ahead and not do this. I got 0.1, y is 0.2, and z is 0.3. If I do x plus y, I get 0.3, and if I do is x plus y equal to z, I get false, okay? And you can say, well, is 0.3 equal to 0.3? That's true. What's x plus y? That's 0.3. Is x plus y equal to 0.3? And it comes back false. Okay, so what's going on here? the problem is that if I change my options to digits equal 17, this will reveal a little bit of what's happening, okay? So x, which was 0.1, in the computer is actually not exactly 0.1, but it's stored as 0.1000001, okay? And point y, which is 0.2, is actually stored in the computer as something a tiny bit different, okay? And so when I do x plus y, I get 0.30000, this gives me a 4 at the end, which feels a little strange. This doesn't seem to work out, but that's what happens when we add these two together in the computer. And z, on the other hand, when we say z is equal to 0.3, it's actually 0.299999999, okay? And so when I ask, is this thing equal to this thing, the computer comes back and says, no, they are not equal, okay? And the problem is that because computers use binary, okay, and everything's represented with a 0, 1, it can only really represent powers of 2 and combinations of powers of 2. So it can represent things like 1/2 and 0.25 easily, because that's, you know, 2 to the -1 and 2 to the -2 and things like that. But it cannot represent values like 0.1 or 0.2 or 0.3. It can only represent those with approximations. In the same way that on a decimal calculator, we are not able to represent 1/3 or 10/3. It gets represented as 3.333. In the same way, in binary, we cannot represent 0.1 exactly. It gets represented with an approximation. And 0.2 is represented with an approximation. And it turns out that when you combine those approximations, you don't get an equality, okay? You get something that it's a little bit different, right? The binary approximation of 0.1 plus the binary approximation of 0.2 is not equal to the binary approximation of 0.3. That's what's going on. And so these are just things that we have to keep in mind. This is the reason why a lot of times when you calculate the mean, like, so one of the things you learn in linear regression is that the residuals have an average, have a mean of 0, right? You do your things, you do your calculation. And then and you might find that if you take your column of residuals and you ask for the mean, you don't actually get 0. You get something like 3 times 10 to the -15 or something like that, okay? And that's, so mathematically it should be 0. But again, because we cannot represent these numbers exactly and we're getting just approximations of things, we get something that's not quite 0. We get something very small, 10 to the -15. But 10 to the -15 is quite different from 0. Okay, so just a quick review to count in binary. I know a lot of you guys already know this, but some of you never learned this. And so in binary, here I'm just using 4 bits here, so 4 places to represent some binary numbers, okay? The first place is the 1s, and then each place is a power of 2. So this is going to be, the second place is the 2s, this place is the 4s, and this place is the 8s, okay? So if I use 4 bits, I can represent up to 16 different values. 2 to the 4 is 16. I can represent 16 values. So we go, 0, 0, 0, 0, or just 0 for 0, a 1 for 1, and 2 is represented as 1, 0, okay? 1 in the 2's place is 0 in the 0 place. 3 is going to be the combination of 2 and 1. 1 in the 2's place and 1 in the 1's place. 4, you get a 1 in the 2's, 4 place and 0 in the 2's and 1s, and it just goes 1, 0, 1, 1, 1, 0, 1, 1, 1, okay? And then when we come over to this column, okay, where we have 8, 9, 10, 11, 12, up through 15, it's actually exactly identical to this column, except we've changed the leading digit from 0s to 1s, because that leading digit represents an 8, and we can think of 9 as 8 plus 1, 10 as 8 plus 2, and things like that. So we're just taking 8 here, and we're just adding everything over on the left, okay? And then if we wanted to keep going to 16, it would be basically identical to this table, but we would have a 5th digit in the front, okay? That would be a 1, and then it would start off with 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and things like that, okay? And so on and so forth. So we are just counting in binary. Okay, and so in order to represent a whole bunch of different values, the computer uses what's called a floating point system, okay? Anytime you have type double, which is your default numeric type in R, that is a floating point number, okay? And floating point is basically just scientific notation. So that is, every number is represented with a mantissa, and the mantissa is, you know, some number. In decimal, the mantissa has to be some number less than 10, okay? And in binary, the mantissa will have to be some number less than 2. And it's, in decimal, scientific notation is m times 10 to some power n. And for binary, it's going to be n times 2 to some power n, because we're using a binary system, okay? All right, and so the rest of today and probably Friday, we will look at the IEEE 754 specification of floating point numbers. So this is, in the beginning, when there were a bunch of different companies making computer chips, they had different ways to implement floating point things, and so the IEEE, kind of the engineering organization, said, you know, we need a standard so that all the computers will kind of work the same way. And so they came up with a system, and they specified it in 1985. There was a revision in 2008, but pretty much it's exactly the same as 1985, but they clarified a few things. So we'll just, the article, Wikipedia article on IEEE 754 1985 is very good, and we'll take a look at all of that. Okay, so now I'm going to switch to handwritten notes here. Okay, I know, right? So what is this? This is week 6, Wednesday. Okay, and I hope my pen works here. Okay, so what we will do is we will use what's called a mini float, all right? So, well, okay, let me just backtrack, okay? IEEE 754, the type double, uses 64 bits. Okay, it uses 64 bits to represent a number. And those bits are split into kind of 3 parts. You have one bit for the sign, either positive or negative, okay? 1 bit for the sign, okay? 0 for positive values and 1 for negative values. And then you have 11 bits for the exponent. And the remaining 52 bits for the mantissa, okay? And so it uses 64 bits or 8 bytes of computer memory and storage to represent a number. And this is what we do. Okay, now we are going to illustrate kind of how this works, but with a mini float using only 8 bits. Okay, so we will have 8 bits. We're gonna split it up in the same way. We've got 1 bit for the sign. We're gonna have 3 bits for the exponent. And 52 bits, oh, not 52, 4. 4 bits for the mantissa. Okay, so we might represent, I'm going to just write kind of spots for our 8 bits here. Okay, and so this part is the, this part's the mantissa, this is the exponent, and this will be the sign. Okay. And so in kind of binary scientific, we have m times 2 to the n, okay? And so let's say we have a decimal value of 1/2. 1/2 is equal to 0.5, okay? How would we represent this in binary?
1 times 2.
Yeah, so this would be 1 times 2 to the negative 1. So this, well, this becomes, I'm sorry, this is binary scientific. Let's just, so in regular old binary, this is 0.1, right? Because you've got, so this would be the ones place, this would be the 2s, and this would be the 4s, and this would be the halves, the half, the quarter, and the 1/8. Is that okay? So this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the negative 1, 2 to the negative 2, and 2 to the negative 3. Okay? And so, and this becomes, this is now a binary point, not a decimal point, but a binary point. Okay, but I'll just call it the dot or the point, okay? And so 1/2 in binary is 0.1, okay? And in binary scientific, this would be equal to 1.0 times 2 to the negative 1. All right? If we had the decimal number 0.75, this is equal to 3/4. This is the equivalent of 1/2 plus 1/4. Okay, so in binary, this would be equal to 0.11, and in binary scientific, we would get 1.1 times 2 to the negative 1 because we've moved the point over basically one spot, right? Is this okay? Representing these numbers with converting them to kind of this binary scientific form. Let's just try like another example. If I had, let's say I wanted to represent in decimal, I want to represent 6.625. Okay, so this is in broken down. This is into powers of 2. We have 4 plus 2 plus 1/2 plus 1/8. Okay, so 4 plus 2 is 6, and 1/2 plus 1/8 will give me 0.625. So in binary, oops, I don't know what just happened there. So in binary, this would be what? 101.101, right? We have 1, 4, 1, 2, 1, 1. I mean, 0, 2 is 1. No, I have this wrong. 1, 1, 0. Okay, a 4 and a 2, and no 1s, and then a half, no quarters, and an 1/8. Okay, so this would be 110.101. Is that okay? And so in binary scientific, this would become what? 1.10101 times 2 to the 2. I'd have to move this over two spaces, okay? But this is obviously, because I'm using the number 2, it's in decimal, right? Not 2 to the 1, 0. But, okay, is that all right? This idea of representing things in binary scientific. Okay, and so the idea here is using our sine, exponent, and mantissa, we are going to represent these, represent values using kind of mini float, okay? So in our mini float, we have we have 3 bits for the exponent. Okay. So how many unique values can I represent for the exponent? Yes, question. Up here? Yeah, so I'm just copying, so right here I have 110.101. And then so I'm copying this. So to go into scientific form, we're just moving the decimal place over. You have a 4 and to get the 6, it's the 4's place and the 2's place, and 0 and the 1's place. So it will be 4 and 2. So 6 is 110 in binary. 5 would be 101. I'm pretty sure. I can we can double check later. But okay, so for the mini float, we have 3 bits for the exponent, so we can represent 8 unique values. Okay, and our 8 binary values are going to be 0, 0, 0, 0, 0, 1, 0, 1, 0. I'm having trouble here. 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, and if I just did the regular decimal representation, I would be representing values from 0 to 7, okay? But I want to be able to represent positive exponents and negative exponents, okay? And so what we use is we use what's called a biased scheme, where we just say, you know what, let's shift our numbers over, and this, so I guess, so I'll call this, I'll write regular decimal. Regular decimal, this would be 0, 1, 2, 3, 4, 5, 6, 7. That's regular decimal. Okay, this is only positive numbers, okay? So what we use is a biased scheme, and we just subtract 3 from everything. Okay, and so now I can represent 8 unique values going from -3 to +4. Okay, so the biased scheme shifts basically where our 0 is. Okay, and so here our bias is 3. And now we can represent both positive and negative values. Okay. In general, the bias will be two to the n minus 1 minus 1, okay? N being how many bits for the exponent. So for 3 bits, if n is equal to 3, we have 2 to the 3 minus 1 minus 1. So we have 2 to the 2 minus 1, which gives me 4 minus 1. Bias is 3. Okay, and that just means you take the regular decimal values and you subtract 3 to get your biased scheme representation. Or if you want to go from the biased scheme representation back to decimal, you add 3 and you turn it into binary. Okay. So so that's the exponent part. And now we have 4 bits for the Mantissa. Okay. And if we're in binary scientific notation, okay, when you write something as something point something 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 times 2 to the n or whatever it is, okay, this leading digit will always be what? It will always be 1, right? Because in scientific notation, your leading digit can't be a 0. And in binary, you don't have any digits other than 1. Okay, so the leading digit is always 1. Okay? In scientific, the lead cannot be 0. And in binary, there's only 1. There's only 1. You can't put a 2 or a 3 or a 4 there. Okay. So with that, we can always assume the leading digit is 1, and now I have basically I don't have to waste putting a 1 here. Okay. I can just say these 4 values, the 4 spaces, now represent spaces after the point. Okay, so so now I can assume this is always a 1, and my 4 Mantissa bits are going to just represent the values after the binary point. Okay. Okay, so let's just try to put this together. Let's say we've got a value that goes like this. For the sign, the exponent, and the Mantissa. Okay. So with the Mantissa, we can say this is going to be 1.0111 times 2 to some exponent value. Right? All right, and what is our exponent? Okay, so our exponent is equal to 101, which in regular decimal is equal to what? So in regular decimal, 101 represents 5, okay? And then we apply the bias. And how much is the bias? We're going to subtract 3, so our exponent is going to be 2. Right? So this becomes 1.0111 times 2 to the 2. Right? So this is equivalent to being, well, we have a few ways to do this, okay? We can say this is we're gonna move the point 2 spots over. So we're gonna have 101.11, and this becomes what? 4 plus 0 plus 1 plus 1/2 plus 1/4, and we get the value 5.75 in decimal. Yes, question?
Would the leading one being the one stoppers from representing 0?
Hmm?
Would the leading one being the one stoppers from representing 0?
Yes, that's a very good point, okay? And we'll get to that. But that's a very good point, okay? We could also do it the other way, all right? And let me just say 1.0111 times 2 to the 2. This is, you can also think of this as 1 plus 0 plus 1/4 plus 1/8 plus 1/16 times 2 to the 2. Okay, and so when you multiply this out, this becomes 4 plus 0 plus 1 plus 1/2 plus 1/4. And we still get 5.75. Okay. Let me just mention the sign bit, okay? The sign bit is 0 for positive and 1 for negative, which means every value can be represented either the value that we can make up with the other 7 digits will have both a positive and a negative representation, okay? So any value we make with the other 7 bits will have both a positive and negative version, okay? And so a side effect is, you know, when we represent 0, we will have both a positive and a negative 0, okay? Okay. That feels a little bit strange because there's only 1 0 in the real number system, but in computer numbers, we've got positive 0 and negative 0. You can kind of think of it as 0 approaching from the right and 0 approaching from the left. It's not exactly that. They're both just positive and negative 0, but you know, maybe it's easier to think of it that way. Okay. We haven't gotten to how to represent 0 yet, okay? And I think we'll have to wait till Friday for that. In the meantime, though, we do have a few special values here, okay? Okay, so if all exponent bits equal 1 and all Mantissa bits are 0, this is infinity. Okay, this is our computer representation of infinity, okay? And you can have this. So this is equal to infinity, and this is equal to negative infinity, okay? Or at least the computer representation of infinity. We also have, if you have basically all ones here, and then something other than all ones. I'm not all 0. Something other than all zeros. So this is not all 0. Then this becomes a nan. Okay. So nan just represents basically not a number. So you've got a bunch of representations for nan with our bits. You can have 1, 1, 1, 0, 1, 0, 0, or 0, 1, 1, whatever, okay? So this is not a number. So all nans are going to be type double because it's got to be represented this way, okay? And so you have things like, I think 0 over 0 will result in nan. I think infinity over infinity results in nan. Oops, how do I do? Inf? Oh yeah, no. Capital I. Okay, there we go. Inf over inf becomes nan, things like that. I think, yeah, okay. But, so you have infinity, positive infinity, and negative infinity, and things like that. So 0 over 0 is nan, and then inf over inf is nan. There's a bunch of stuff that results in nan. Okay, so we'll stop here. We'll talk about representing 0 on Friday, and we'll look at more of this floating point stuff here. Okay, see you guys then.